4.5 Libby Ferguson Quantitative Data Analysis Techniques, Part 1. When you organise your quantitative data, there are 4 methods that you can use. So you can use the range, rank order distribution, simple frequency distribution, and group frequency distribution. According to Adams et al. 2010, range is the distance in numerical value from the highest to lowest value collected, and you calculate the range by subtracting the lowest value from the highest value. So for example, in my data, the highest value is 2.16, the lowest value is 1.46. So therefore the difference between them is 0.7. Having a range on its own doesn't mean anything, as we don't know if it's a significant difference or not. With the range, you may also have an anomaly in your data, either as the highest result or the lowest result, which could mean that this piece of data isn't similar to the others and stands out, meaning the range would be inaccurate. So rank order distribution. So according to Adams et al. 2010, rank order distribution means placing your data into an ordered list from the lowest to the highest in a single column. This sort of data organisation is only efficient if you have less than 20 values of data or it gets too long. It can be useful to put your data into rank order before you work out the range, so the highest and lowest values are clearer to see. The next part is simple frequency distribution. So according to Adams et al. 2010, you use simple frequency distribution with a table that has 2 columns, one for the raw data and one for the frequency scores. The frequency column is the number of times that particular score is achieved. Simple frequency is only used when there's more than 20 participants and the range is less than or equal to 20. So group frequency distribution. So according to Adams et al. 2010, group frequency distribution is when the table has 2 columns, raw data and frequency scores, except this time that the raw data column is for group data rather than individual. The other column is still frequency. Whilst there aren't more than 20 participants in my data, group frequency distribution is used when there's more than 20 participants and a range that's greater than 21. As well, the ideal number of groups is 15, however I only have 5. But to work out the range of the groups you need is calculated by the range, and it's divided by the number of groups you want, which is ideally 15. So this method is good for organising and presenting large amounts of data, however you lose information through this process. So once the data is in the groups, it's impossible to work out the individual scores. So for example, there is 5 values in my 500 to 599 category, but from this data you can only tell that 5 athletes fall into this category, but you can't tell what their individual scores were. This is part 2. So my first graph is a scatter plot graph. So scatter plot graphs are used to see the correlation or relationship between 2 things. Each dot on the graph represents a person and their 2 scores. So on this graph it would be flying sprint speed and static sprint speed. As you can see, the general trend is that people's flying sprint speeds times were quicker than their sprint times. The graph also contains an anomaly, as one person got 7.26 seconds on their static sprint time. This score doesn't fit in with any other results and also isn't similar, meaning it is an anomaly. The graph is a line graph. So a line graph is used as a comparison between 2 sets of data. In my example, I compared the flying sprint speed times with the static sprint speed times again. Along the x-axis is the number of participants in the study, and along the y-axis is the sprint time in seconds. This way of comparing data makes it clearer to see the differences in the results more easily. On my line graph, I have also added standard deviation bars. These are calculated with the mean and standard deviation. For static sprint speed, however, the bars large due to the anomaly of participant 11. So the next graph, as it were, is a table. This is where you can insert all your raw data, as you can see here. If the table is quite large, in a research article, it could be found in an appendix at the end. As well as having a table for all the raw data, you can have tables for summary data. So on the right, I have a table for the mean, standard deviation, median, mode, maximum, minimum, and the range for my static sprint times and my flying sprint times, as it's just an easier way to see all the results in one place. The next graph is a bar graph. So bar graphs are used to compare data between two groups. My graph shows the different heights 14 participants jumped in centimetres. Bar graphs also make it easy to understand the graph at a first glance. As you can see in my graph, participant 6 is the highest and participant 2 jumps the lowest. The next graph is a box and whiskers plot. So a box and whiskers plot can give you 5 pieces of information. So first it will give you the median. This is the vertical line in the box, as seen here. Next it shows you the upper quartile, and the upper quartile is the top 25% of the data. Next is the lower quartile. The lower quartile is the bottom 25% of the data. So this is where the median is. And then, as you can see here, this is the upper quartile and the lower quartile. So in my example, for systolic blood pressure, which is the orange graph, the median was 130. The upper quartile for diastolic blood pressure was 80, and the lower quartile for diastolic blood pressure as well was 59. Finally, on box and whiskers plots, you can find the maximum and the minimum piece of data. So these are marked by the 2 lines outside the box. With these pieces of data, it helps you to find the range. So the next graph is a histogram. So a histogram is much like a bar graph, however, a histogram presents a set of continuous data, so there are no gaps between the bars. So with the frequency on the y-axis and the numerical values go on the x-axis. So this type of graph is used to show the frequency of data. So the higher the bar is, means the higher the frequency. With more results in a graph, it should look more like a bell curve, with the highest frequency in the middle. So this is a normal distribution curve. As previously mentioned in a histogram, which should have looked like a bell-shaped curve had it have had more results. This is an example of what a bell-shaped curve would look like. So normal distribution curves all have a similar shape, which is the bell-shaped curve. The line down the middle at 0 represents the mean of the data, as well as the median of the data. So standard deviation is a measure of spread. If there is a low standard deviation, then all of the results will be clustered around the mean. However, if there is a high standard deviation, then the results will be dispersed over a wider range. No matter what the standard deviation is, if you move one standard deviation up or down from the median, you'll get to 1 and -1. So 68% of all observations within your test lie within this area. If you then move one more standard deviation away from the median, you will get to 2 and -2. 95.44% of all observations fall between these two values. And finally, if you move one more away, again, you get to 3 and -3. So 99.72% of all observations fall between these values. The standard deviation shows how significant a value is depending on how far away it is from the average. So between -3 and -2, or between 3 and 2, there will be 2.14% of observations, meaning it has a higher significance. This graph can also help make an educated guess as to where they will go depending on the results as the graph follows a trend. Standard deviation is different for each piece of data set, depending on the standard deviation being high or low. However, they should all follow a bell-shaped curve. Excuse me. They're all continuous data and they are all typically symmetrical. Before, I said the normal distribution curve should always be typically symmetrical, like the graph in the middle here. However, the two graphs on the outside are both not symmetrical. So this is what happens when you get a skewed or asymmetrical curve. So the negative skew on the right is always presented as the long tail would be towards 0. So imagine 0 would be here. This is showing a negative distribution. Or if you go to the other side, so the positive skew, the long tail should always be to the right, so away from 0. And this is showing a positive distribution. But they are both not normally distributed. So next we're going to talk about outliers. So an outlier is a piece of data that is much higher or lower than the rest of the data. So it doesn't fit in with the trend of the other data. When you have an outlier in your data set, it can skew your data. So that will make your graph look like either the positive or the negative skew here. Your data and so therefore the outcome of the sample and population will be different. There are two ways to get rid of outliers. So you have trimming and windsoring. So trimming is the process of removing the data points from analysis that are unlike most of the data in the set. So as you can see here, I have a set of data. So it's 2, 3, 3, 6, 7, 9 and 21. So 21 doesn't follow the trend as all the rest of the numbers are very similar in size. So with the process of trimming, we just remove the 21. Next is windsoring. So this process is when you have a legitimate outlier that can be modified to become the next nearest or acceptable value. So here we have 4, 14, 15, 16, 17 and 33. So here 4 and 33 are both outliers, as they are not similar to the rest of the data. So with 4, the next nearest data is 14, as it's the next in the set. So this 4 would turn into a 14. With the 33, so just like with the 4, so the next nearest set in the data is 17. So this 33 would then change into a 17.